Hello and welcome back to Calculus 3, yes. Section 13.5. We might do this in two runs. We have about 30 minutes, so we should be good to take care of cylindrical integrals at least. And next week, next class, which is Wednesday, we'll continue. So, upgrade in mathematics. You've seen it many times. Everything is about upgrades and generalizing. So you've seen single integral get upgraded to double, get upgraded to triple. Dx went to dA, which was dx dy or dy dx, and then dv, dx dy dz. And now on the base of the polar coordinates, which were r theta, we are going to introduce cylindrical coordinates and spherical coordinates, which are the 3D upgrades to the 2D polar. So polar coordinates, which were r comma theta, which was a 2D thing, are going to break into upgrade. Cylindrical coordinates, which is 3D, and that's going to be r theta z, or spherical, which is r theta phi. What happened? Two angles, yes. So let's talk about cylindrical first. So we are going to draw the cylinder. And I'm going to draw representative d theta here. Observe that the volume is base times the height. Now this is base, which is the area. Now I know that I can get that area using the double integral alpha to beta, and then let's say 0 to or then a to b. Let's do a to b of r dr d theta. Which was the double integral, and you know that when you integrate this r, you get r squared over 2, which was the single integral. If you remember the single from Calc 3 section 10, you had this formula, right? Well, that formula was just Calc 3 formula integrated. When you integrate r, you get r squared over 2. So now we see that the base is double integral from polar coordinates that was introduced last class. And we are going for the volume now to introduce another integral for dz inside. So now I'm going to have alpha and beta for d theta at the end. I'm going to have r1 to r2, which are the radii for dr. I'm going to put this r stained in blood so you don't forget it. There, for dz, we have a to b, which would be our height. So this integral will compute the volume of the cylinder, and again, you can put in some kind of function inside if you have something in addition to compute. And how it works is the representative pizza slice in our domain, which is d theta, is going to make a full revolution from 0 to 2 pi, and that's your alpha and beta outer integral. Or maybe you need a quarter of the shape or a half of the shape or whatever part of the shape, in which case that theta will be stuck in between two angles that are bounding the motion. You also have from the center all the way out for the radius r, which could be for the circle, the entire thing, which is 0 to whatever the hell radius is. Or if you have the annulus like this, r1 to r2, so that's if the object is hollow in the middle. So the base for these things is, well, in this case, it's a circle, right? But then again, don't ever lose sight that these puppies here, the first two integrals, are polar, right? Which means that whatever shape it can be described by the polar could be there. Cardoid, flowers, all the other things that we did in class in Calc 2 or Calc 3. So now, what you see there is a rectangular region integral. It's not general because this one provides you with, since you have A and B, cylinder that has flat top and the flat bottom because I just have A and B. Remember that your floor over here is z equals 0, ceiling is z equals 10. Those are numbers. Surface of this desk, z equals to 3, right? 3 feet tall. So when you have A and B for dz, you are talking about flat edges. But then you can have a cylinder that has a flat edge on the bottom and some kind of z equals a shape on the top, which is what we've seen in a previous section, right? With having paraboloid or hyperboloid or whatever else, right? You can also, you can take a sword and cut this, you know, at the angle. That would introduce the plane on top, right? So you can have equation for that plane. It could be paraboloid again, right? Or any other shape. So the A and B, when they are numbers, we are talking about the general, easy to deal with. The rectangular, right? Easy to deal. But then we can have functions there as well. And then also general versus rectangular, right? The rectangular meaning the basic one, where your alpha and beta will always be alpha and beta there, but angles. But then R could be functions, right? If you're following a stencil, like a flower stencil or a cardioid or something like that, circle, right? Can have anything. Now, before we actually do integrals, I just wanted to build really quickly how the integral works. To understand cylinder, I hope you have no issue with, you know, visualizing what I already did for the integral, and that is that you have your, let me just draw this, x, y, and z. You have coordinates to be r, theta, z. So that's the cylindrical coordinates, and the conversion works the same way as the polar. So conversion is polar plus z equals z. It's kind of lame, but that's true. So polar stuff will take care of the conversion x and y, which is the domain, so x and y into the r theta, and then z equals z. Z equals z remains the same. So all of the conversions that you know from before remain exactly the same, which is why I was able to so quickly convert the previous problem. I knew x squared plus y squared is r squared. So x squared plus y squared is r squared, and if you remember that the inverse tangent of y over x is equal to theta. So those conversions still stand, and then z equals z, right? So that's the conversion pair. So conversion is just a regular polar conversions plus z equals to z. And you get your cylinders. We also have the other way to convert, which is x equals r cosine theta, y equal r sine theta, and again z equals z. So that's to go the other way for conversion. My hope is that you guys will spend time to practice this with conversions. I already defined the integral, but now I'm going to write the actual cylindrical coordinates integral. So triple integral in cylindrical coordinates, and that would be triple integral over region d of some function x, y, z dv will be, and now we have the function alpha and beta on the outside, which corresponds to d theta. Then we have our g of theta and h of theta, which allow polar coordinates to either be basic circles or the most complicated awful things. And we are introducing capital G. Now these are x and y, but we are converting them into polar. So x is r cosine theta and y is r sine theta, and capital H, which is again of x and y, which is r cosine theta, r sine theta. And then we have our good old function f of xy, but then again not allowed to use xy. We have r cosine theta, r sine theta, and then we have good old z dz, r dr d theta. I'm going to just underline this r a little bit here so you don't miss it. What an awesome formula. So easy, because this is your polar stuff you know from before, and this is just g of xy, but written in terms of polars because you have to integrate everything out in terms of polars, right? Z is the first one you're integrating, and you still have to go integrate in terms of r and integrate in terms of theta, and you have x and y. You can't do it, right? So you have to convert those into these as well, which is what you saw me do last lecture. You see how my inner integral here does not contain x and a y. It's everything is in terms of r, because I am yet to integrate. The original integral had x's and y's, and I just said x squared plus y squared is r, so r squared, or I was supposed to say plus 1 there, and this is 19 minus. When you factor out minus, you are left with x squared plus y squared is r squared, so 19 minus r squared. I have to fix this now. And when I travel back in time, I'll tell to my past self not to make this mistake. So let's, I just wanted to say x and y and x and y, so that you know that you are converting those to use the formula in peace. Yeah.
So before we had g of x and h of x, why isn't it g of r and h of r? R cosine theta.
Because if you take a look at your input, the input integral is a to b, and then this is f x y z. Let's say the z dy dx. So this one over here is g of x, and this one is h of x, and this is capital G x y, and this is capital H x y. These two integrals have to be the same thing. These two integrals are the same thing. Now, I am swapping this integral, these two integrals here, with these integrals here, which give me the polar coordinates. So, good old xy input into a polar coordinates input. Now, when you take a look at this is given in terms of x and a y. Right? So I have to convert x and the y, which are converted using that.
The other x doesn't have to be converted that way?
All of x's are converted. I don't see any x's in this problem here. What happened?
How are you switching the first two integrals?
I'm switching it through the polar coordinates, looking at the so you can't, you're not swapping x with theta and r with y, because I think you are alluding to that you want the first integral, which is x, to be now d theta. It is not one-to-one correspondence. It is x and y together change into theta r together. So the integral that used to be x1 to x2, y1 to y2, and z1 to z2 is now changed to theta 1, theta 2, r1 to r2, and z1 to z2, but in terms of r's and thetas, because we're not allowed to have x's and y's anymore. And it's not one-to-one because all of these things depend on each other. We have that x is equal to r cosine theta, right? X is not just theta. X is r and theta combined, because it is a completely different way to get to the same point. Together, they act as a pair, as you can see, because these guys are the same. Z is equal to z. So you are swapping it as these first two integrals are a unit, because your good old input that used to be xy is now transformed, well, it's still graphed on xy, but now it's circular when it used to be rectangular. Sounds good?
Yeah.
And obviously we need to do just 5,000 problems, so it'll be clear. Hopefully. And hopefully you'll do another 5,000 when you get home. I mean, what are you gonna do tonight? Go home, crank like 3 or 4 of these, go to bed by 2 p.m. Next day, fine. So all right, so the first problem they are explaining in the textbook, and I like it, is the half of the cylinder. So we're going to take this this cylinder, think of a soda bottle or something, take a sword and just, or an axe, right, and right down the middle to create the half, right? So what I'm going to do here is I'm going to have something like this. I'm not too much of an artist, but I hope you can see. So this is half of the cylinder. This is y-axis, this is x-axis, this is z-axis. Half of the cylinder. Say this is 3 inches and the height is 5 inches, whatever. Okay, so I'm going to set up 2 integrals here because I can. We're going to set up the rectangular one to practice previous lecture, but we're not going to compute because that one's a living nightmare. And we're going to also put the cylindrical one, which will be a joke to compute. So let's go with the rectangular integral first, because rectangular integral, we just set it up, but we're not going to solve. So I have 3 integrals there. I'm just looking for volume, so I'm not going to put any function in there. And if I draw my dx, which I will have to erase, dx goes on the outer, and then you have dy, and then you have dz. You see that dx goes from 0 to 3 because it's only half of the circle, right? And then y's, we have negative square root of 9 minus x squared and positive square root of 9 minus x squared, because that's what the top and the bottom of the... So let me draw this half of a circle this way, and when you put your dx, I hope it's clear, right? We're moving from 0 to 3 on the x-axis, and you have a square root of 9 minus x squared and a negative square root of 9 minus x squared, because that's the half circles, right? Formulas. It's x squared plus 9 plus y squared equal 9, right? Solve it for y's. And then z's, easy. 0 to 5, it's a flat bottom and a flat top, right? 0 inches and 5 inches. So done. The soda can is cut in half vertically. Now, in order to solve this, well, obviously dz is easy, right? You will just be integrating 5 in terms of y, so you get 5y. But then you get 5 square root plus 5, you get 10 square root of 9 minus x squared. And to solve that, you will have to use trig sub, right? And that might not be a preferable way to do this thing. So what I'm going to do instead, I'm going to draw representative pizza slice d theta and set this up as the cylindrical, triple cylindrical integral, which I'm not going to put the function in there because I'm looking for volume, my v equals, which has string as dz, r, dr, d theta. Let me just make sure that I underline this r here. So now I'm looking at this and I'm trying to figure out where this stuff goes, right? So d theta is this representative pizza slice, which is going to start here and go around there. So what are the angles that it covers? Nope. Negative pi over 2 to pi over 2. So if you are to draw the same thing like this is your x-axis. Representative pizza slice starts here and goes up to there. So negative pi over 2 to positive pi over 2. If you need to draw the domain the way you can see it, do it. Just do it. I can't hold it. Yes. All right. Enough of that. So now we have d theta, which, dare I say, clearly goes from negative pi over 2 to pi over 2. We have radius r, no brainer, 0 to 3, right? And z, 0 to 5. Which one do you want to compute? Yeah, you want to compute the new one, right? Because the new one is easy. Now, if you are to make this using polar coordinates worse in any case for this, it will be exponentially worse for that one. All right? So making it worse for polar coordinates will make it much worse for rectangulars. These two worlds, and I'm telling you this for the 50th time in this course, polar coordinates and cylindrical and rectangular and spherical later on, they don't compete against each other. They complement each other. Just like we have different jobs in the world. Someone is a cop, someone is a teacher, someone is a criminal, right? We have different ways to deal with different situations here. All right, so to integrate this is just a joke now. So dz, that's going to be 5r, dr, d theta. Which is negative pi over, right? So that's pi r, so that's pi r squared, so pi 5 halves. So 45 halves. And it's 45 halves times pi. 45 pi over 2, right? I skip some steps. You can fill in the blanks. Next lecture, after this, we still have to finish examples, is going to introduce a concept of the mass, which is the density function integrated. So integral is going to give it a shape and have a density function, and you compute the mass of the object that way. So a triple integral of rho, we'll use rho for density function, is going to give us mass of the object. An entire 13.6 deals with 1-dimensional, 2-dimensional, 3-dimensional center of mass calculations, which are extremely important if you want to design cars and trucks and airplanes and stuff, because center of mass is one of the very important things. You don't want it to have too high. It flips, right? If you have a center of mass for the truck very high, it's going to flip every time you take even the slightest turn. So you have to figure out distribution of mass in whatever you're designing. So we'll be dealing with that. One more example from homework, and since we only have 3 minutes, I'll work on it directly, and then we will finish this next time. So let's say you have, so problem 30. This will be fairly quick. So you have a ball like this. X, Y, Z. This is at 25. And we just have a regular paraboloid here. Z equals x squared plus y squared. All right, we're going to set this up immediately. If I shine the light, it will give me this circle in the plane whose radius is 5, because you have a flat top. Flat top means the plane at the height that it's provided to you. So the top function here is z equals 25. And by simply equaling two z's, we get x squared plus y squared equals 25, which is 5 is the radius for the circle. That is your region. I want the entire thing, so 0 to 2 pi. And radius is 0 to 5. I have my dz, r, dr, d theta. And the z is, the top is 25, so that's easy. The bottom is r squared. Very good. So convert z equals x squared plus y squared to polar. So how do I convert it? Well, z is equal to z. I don't have to worry about that. And x squared plus y squared is equal to r squared. That's basic conversion that you must know from your chapter 10 or you're doomed. So welcome to Calc 3 and prerequisites. So now I know that this one is r squared. That's the bottom of the shape. And the top of the shape is the flat z equals 25. So it's from the bottom up, right? So from r squared to 25. And all I need to do now is to integrate this mess, which should be simple. dz, so that's going to be 25 minus r squared times r dr d theta. So now you will distribute r, get 25r minus r cubed dr d theta, integrate in terms of r to give you 25 over 2r squared minus 1/3 r cubed, computed from 0 to 5, still d theta. Plug in 5, that's 625 over 2 minus 125 over 3, still integral 0 to 2 pi d theta. Common denominator is 6. So 3 times 625, 1875 minus 250 d theta, which is a constant. That's 1625 over 6. Let's see, 11 and 3 is 14, not divisible. All right, so that integral d theta, which is 1625 over 6 times 2 pi minus 0, who cares, is equal to 1625 pi over 3. What happened? I have no clue what you're talking about. 600 times 3 is 1800. 25 times 75, so 1875. Minus 250 is 1625. Yes, right.
Is that the 1/4 of the arc of the chord on the first?
Do what?
Yeah, you didn't integrate it.
Oh my God! I looked at this and and it looked like a 2. Why don't you say so? Now we all have to sit here another 40 minutes until I fix this. Where are you going? Sit down. R to the 4th, that's 625 over 4. So now it's 625 over 4, and that's 625 over 4, and that's 625 over 4, and that's 625 over 2. Much better. Yeah, that 3 looked bad, so I thought it was as a 2. It's a 3. There we go. There we go. All fixed. Thank you. So see you all in 2 days. We will finish this lecture next time. See ya.